Welcome back. In this video, I'm going to walk you through the entire RAG pipeline from start to finish. I'm approaching this from the perspective of someone who's gone from a cloud and systems background into building AI-powered systems. So the explanations are intentionally beginner-friendly for cloud engineers and backend developers. By the end of this video, you should have a clear understanding of how RAG systems work. We'll cover what chunking is, why embeddings exist, how vector databases work, and how retrieval fits into the overall pipeline. I'll explain why each of these pieces matter and what can go wrong at each stage, and how those design choices affect the final answers you get from the model. So let's start. Before we talk about RAG, we need to be clear about what large language models know and what they fundamentally don't. Large language models are trained on vast amounts of general and public data, which makes them very capable at language and reasoning. But that also means they fundamentally don't know anything about your specific systems, your internal documentation, your code bases, or your business logics. If you ask a model something like, how do I set up authentication in our corporate application based on our internal docs? The model has no idea, not because it's weak, but because that information was never part of its training. Prompting harder doesn't solve this. If the model hasn't given the information at inference time, the best it can do is guess, and those guesses often sound confident even though they are wrong. This is the gap that RAG is designed to fill. RAG doesn't retrain the model. It doesn't magically expand its knowledge. Instead, it retrieves relevant information from your own external data sources like documents, your code, your policies, and injects that context into the prompt so the model can reason over real and domain-specific information rather than hallucinating. Once you understand that RAG is fundamentally about controlling what context the model sees at runtime, the rest of the pipeline starts to make sense. Let's follow a single example through the entire RAG pipeline to understand how this works. Imagine we have a small internal code base and we want to ask, how does authentication work in this service? I'll show you what happens to that question at every stage. So let's start diving in. So we start with the raw data. In our case, these are the source code files. But we can't feed the entire file to the model because there are context size limit on the model and the retrieval wouldn't work well anyway. So the first step is going to be chunking. Chunking decides how we break the data into smaller pieces. Maybe we divide by function, by class, or by logical section. If the chunking is correct, only then the retrieval returns everything to fulfill the request. For example, if authentication logic is split across multiple chunks, the retriever might only returns half the story. So it's very important to get this section right. There are many ways to make the chunking effective, but we are going to cover only one method, which we will cover later in this video. Let's move to the next part. Once we have chunks, we convert each chunk into an embedding. An embedding is just a numerical representation of the meaning. The important point is the embedding doesn't store text, it stores semantic intent. The chunk containing verify token ends up close in embedding space to the question about authentication, security, or token, even if those exact words aren't used. These embeddings are stored in a vector database. Unlike a traditional database, vector database isn't about the rows and the columns. It's about finding the nearest neighbors in vector space. The vector database is optimized to answer one question very fast, which is which chunks are the most semantically similar to this query. Now, when the user question, how does authentication work in this service? The question is also converted into an embedding. This puts the question into the same semantic space as the stored chunks. As I said before, we are no longer matching words here, we are matching the meaning. The vector database compares the query embedding to all the stored embeddings and return the top k most similar chunks. If the chunking and embeddings were done well, the retriever returns the authentication related code. This is the most important point. The model can only answer based on what is retrieved. Next, these retrieved chunks are inserted into the prompt, along with the system instructions and the user question. From the model perspective, there is no such thing as retrieved data. It just sees the text. Alright, now that we understand the theory, let's make this real with code. What I'm going to show is a complete RAG pipeline in a few files. It loads documents from an internal docs folder, chunks them, creates embeddings, stores them in vector database, retrieves the most relevant chunks for a question, and then calls the LLM with that retrieved context. And most importantly, will show both as success and failure modes. Quickly, here is the structure. So internal docs contain the knowledge, the information the model was never trained on. The source folder contains the pipeline code, the loader, the chunking, the embeddings, the retrievals. RAG_demo py is the orchestrator for the demo. The demo is deliberately designed to run into 4 scenarios. One is the clean success case. The second one is a clean refusal when the answer is not in the docs. The third one is the retrieval failure by setting top k value too low, which is 1 in this case. Fourth one is the design failure by using intentionally bad chunking. Let's quickly go through our source folder, where our RAG logic lives. So we start with the loader.py. This file is responsible for loading documents from the internal docs folder. It walks the directory, reads the supported file types, and returns raw text with metadata like file paths, etc. The pipeline doesn't care whether the knowledge comes from a markdown file or a PDF or a database. It just needs text plus metadata. In real systems, this layer often pulls data from S3 or Confluence, or you directly connect it with SharePoint. Next is chunking. This file defines how the documents are broken into chunks, which is one of the most important design decisions in the RAG systems. For this demo, I'm chunking based on the character size, which is 900. That's simple, easy to understand, and good for learning. But this is not best practice for production systems. In real systems, chunking should be token based or structure aware. For example, by headings, by sections, by function or paragraphs. Character based chunking can cut sentences or concepts in half, which reduces the retrieval quality. We are using it here purely to keep the demo simple and readable. Next is embeddings. It's where the text becomes vectors. An embedding model converts each chunk into numerical representation of meaning. Now we get to vector store. This is where embeddings are stored and indexed in a vector database. We are using Chroma DB, which is running locally and in memory. That's perfect for demos and learning. In production, this would typically be replaced with the OpenSearch, pgvector, Pinecone, or any managed cloud service. So a vector database is optimized only for one thing, which is given a query, find the closest vectors efficiently. So the vector store doesn't generate answers. It just decides what context the model is allowed to see. Next is retrieval.py. It's the retrieval step, which is the R in RAG. We embed the user query into the same vector space and then ask the vector database for the top k most similar chunks. If retrieval is wrong, everything downstream is compromised. Most RAG failures are retrieval failures, not the model failures. Finally, the RAG chain.py is where everything comes together. The file assembles the prompt by injecting system query, the retrieved context, and the user question. Then it calls the LLM using Grok. We now move to the orchestrator, which is our main class. So we import few libraries, OS for the environment variables and Grok for calling the LLM. Then we import 3 pipeline steps. One is build vector store, that's indexing, which is loading documents, chunking, embedding, and storing. The second one is the retrieval, which is semantic top k search. The third one is answer with RAG, that's generation, the assemble prompt plus calling the model. So the entire RAG pipeline is expressed as indexing, retrieving, and generating. Next, we are using a Llama 3 model, and we are also pointing to the knowledge base folder that contains our internal documents, which is internal docs. Next is the retrieval step. The query, which is the user's question, gets embedded. The vector database performs similarity search, and we get back the top k chunks along with the metadata, and that would be our context. Then we print the retrieved chunks here, and we are capping it to 180 characters, so the terminal output is readable. Then finally we call answer with rag. That assembles the prompt with the system instruction, the retrieved context, the user query, and then call the LLM, the model, and prints the answer. Next is our main function. Here we just import the Grok API key, which comes from the environment variable, and then we initialize the Grok client. Then comes this section here, which is a success case. This specific step is the indexing step. We are calling build vector store that loads the document from internal docs folder, chunks them, embeds each chunk, and then stores them in a vector database. Notice we marked use bad chunking as false. That means the index use our good chunking strategy. Also note that persist directory is equal to none. That makes the vector database in memory. For a demo, that's fine, but for real projects, this points to the actual managed vector store. Now we are going to run our first query, which is our success case. And the question is, how does authentication work in this system? And we set k is equal to 4, which is a sensible default for a small knowledge base. So let's run this query first. This is the answer that comes from that file, and it has given the sources as well. We can go to the authentication file and we can see that we have that information here. So that means the model is not guessing, or it's not answering from its own memory. It's summarizing and reasoning over exact chunks that we supplied. So this is the success case of retrieval. Now I'm going to comment this section because we are going to test the second scenario, which is failure. It's a correct failure because we don't have the answer to this query in our documents, which is the question is, does this system support OAuth or SSO login? This is intentionally outside our knowledge base because we want to see the failure scenario, whether it's returning the correct answer. It should say that it's not in the docs, but let's see. So I'm going to run this again. Okay, so here's the output. You can see that the retrieval still returns the authentication related documents, but the model says I don't know based on the provided context. That's exactly what we want. This is a safe failure, and the model is being honest about what it can and cannot support. A production RAG system must refuse confidently. Now let's comment this question and we move to the retrieval failure case. Here we are setting the top k value too low, that it doesn't return the enough information, enough chunks with the retrieval function, so it fails to answer the question. So it's a subtle failure because the top k is very low. We run the function now. Okay, so with k is equal to 1, it was supposed to return only one chunk, which it did. And let's see, look at the answer. Answer is token TTL seconds, which must have come from the security nodes because that's what it has gone through. Yes. This time we are lucky that the one chunk contains the answer, but that's not robust. In real system, retrieval is noisy. With top k too low, you will miss the crucial context and get failures or hallucinations. Okay, let's look at our fourth scenario. So I'm going to comment it out and uncomment our fourth scenario, which is a design failure due to bad chunking. So we are rebuilding the index here, but this time with use bad chunking function equal true. So let me show you what bad chunk text is. So here's what it does. It takes the entire document, the full markdown file, and then returns it as one single chunk. So instead of splitting the file into smaller chunks, there will be a big giant file. So that means in the vector database, each document becomes basically one embedding and one vector representing the entire file. It is bad because the retrieval works at chunk level. When you ask a question, the retriever is supposed to pull back a small, precise piece of text that directly answered that question. So if each document is one massive chunk, retrieval becomes noisy and you don't retrieve the exact paragraph that answers the question. You retrieve the entire document that contains multiple topics and mixed together. So let's go back to our orchestrator, and we are going to run this function and see the output. And look at the response. So the bad chunking is exactly why the answer can become vague and completely incorrect in this case. It's the model isn't failing here. It's doing its best with the context we gave it. We gave it big messy chunk instead of a clean focused chunk, and it returned the answer which is in the protected endpoint. So that's our complete RAG pipeline. Large language models don't become smarter when you just add RAG. They become better informed. And the quality of that information depends entirely on how you design the pipeline, like how you design the chunking, what strategies you are using for chunking, how you are using embeddings, retrievals, and how you assemble the final prompt. When RAG works, it works because retrieval brought in the right context. When it fails to bring the right context, it almost fails because the whole system fails because the system made the wrong information visible or no information at all. So once you understand that, you stop blaming the model and start designing the better system. So it's all about providing the right context to your model at inference time. In the next video, we will cover the RAG pipeline as well, but we will go one level deeper. We look at why RAG still hallucinates even when the retrieval is present, and how techniques like re-ranking, filtering, and evaluation reduce those failures. And that's where RAG starts to feel production ready. Thanks for watching the video. If you like it, please subscribe the channel and like the video, and I'll see you in the next video.